Kirsten, Ebberston. All right?
Yeah.
That come close?
Yes.
She's here all the way from Sweden to speak to us about genetics and inbreeding. So,
Yeah.
give her attention.
Thank you. Hello, guys. You know, I'm from Sweden, and sometimes I have some difficulties in understanding and in speaking. So if there are problems, yeah, then we will try to fix it. Yes. But why is the picture cut? Should we just need to move it over?
I don't know.
20% is lost. No time, no.
That's the one we did just to get it to show both places. But, I think it's going to be a different one. Wait, yeah, come on. Yeah.
There we go.
Yeah, that's correct. Yeah.
I knew what I did, I'd take credit for it.
So this is made. It's pronounced in Swedish. There is no American people who can pronounce it correct. So, Kirsten, Ebberston. And I'm an agronomist, and you know what that is. And I'm a field doctor in animal breeding, and this means that I wrote a thesis on the genetics, not real genetics, it was population genetics, and breeding and such things. So it's more about breeding than on genetics, but I have studied a lot of genetics also. But I know very little of real genetics on bees. Yeah. I have to have something to drink. I always cough when I'm going to speak, you know. Yeah. I must start to explain what all this is about. We keep bees in order to have pollination of our nature and of cultivated crops. And if you say that trees are crops to apples and such things. So this is very, very important as I see it. That's why we have our bees. And of course, for you beekeepers, it's for you to have a basis for your life, to have money, so you can live. But pollination is important. And since I mentioned the word ecosystem, this is what I mean with ecosystem. Living organisms and non-living nature interacting in a self-organizing way. So bees are part of all this, and therefore very important. And of course, there are other bees than our honeybees, as you know. Lots of them, there are hundreds of them. In Sweden we have some 250 so-called solitary bees. And in this country I think you have still more. And they are very, very important for the pollination. And now I want to speak a little about fundamentals for breeding. So we know what we are really talking about when we are talking about breeding. So there must be genetic variation, otherwise you cannot breed. And you must have a phenotypic variation. You know what that is?
No.
But that is what you can see. And register it. So it's weight, it's color, it's all these things you can see. And the genetics, it's behind. You cannot see the genetics. that you can see the genotype. And through the genotype, you can have an imagination of, through the phenotype, you can have an imagination of the genotype. So you have to have a correlation between the genotype, the genes in the animals or the plants, and the phenotype. Something must be common between them. And you have, and this is very important and a difficult thing, you must have a method for estimating the breeding value. So you know what the genes say inside. And when you read papers or books about breeding, you often listen to the word heritability. And this means about the genetic part of the total variation. If there is no variation, then there cannot be any heritability, and you cannot make any breeding. And if the genetic part of the total variation is very big, then you can breed. And then it is easy to breed, because then you can see on the phenotype what you can see. You know that it is a big amount of genetic variation behind. So, and the last sentence here is also important, since many people think that heritability is a constant, like think physical things. In what do you say, physics? Is that correct? No, physics. Physics, yeah. Because if heritability is quotation between two figures. So if you have a big environmental variation or a big genetical variation, it depends on the quotation between them, what heritability you get. So if the environment will not vary at all, then you can see a very big lot of the genes. And if the environment varies very much, then you can't see anything about the genes variation, even if it is there. So it is difficult to know how to estimate the breeding value, to find it, to find the value of the queen of the colony. So all this I'm going to say now is very much to sketch the things about breeding and genetics. So I cannot go very close into it because it takes too much time and I must prepare much more, and it's difficult to follow it also. And then, since we are now seeing that there are problems in beekeeping and there are problems in biodiversity all around the world, then we must find out the fundamentals for sustainable maintenance of genetic populations. All the biological material, of course, is genetic populations. And then we are talking about that if you're keeping a sound genetic variation and a good gene pool, for instance, as we heard just before, then we are talking about the population number. If you have a big population, then you can keep many genes. If you have a small population, you can keep few genes. But the population is that we talk about in this context is what we in genetics call effective population size. And that means a population of a certain breeding structure. So it depends very much on the breeding structure, how big the population really is. So, and we mean with effective population, that is a population with a certain number of individuals mating on an average. So everybody mates to everybody. And each individual has 2 offsprings. That means if there are males and females, every female has 2 offsprings, every male has 2 offsprings, and they mate to each other. And then they have, you have the same number of offsprings each generation. So this is the main sentence of effective population size. And then the species we're talking about, they have different breeding structures, making this effective population much, much smaller than the consensus number of the population, what we can see and what we can count. And if we compare now bees with, for instance, mammals, then we see that bees are very, very different from mammals. And they have, in their natural way of living, they have a very special way of keeping a very large effective population number. And what we do when we breed bees is that we this system so we cannot keep this very, very good system alive. So we diminish the population number. And so in reality, the effective population of all these breeding stations and so on, and breeding companies, they keep a very, very, very small gene pool, which is due to the breeding structure we have when we raise queens and use insemination and mating stations. And yeah, this picture I will explain for myself what breeding is. And breeding depends on that you have genes and you have genetic variation. And from the beginning you must have some sort of evolution giving us more and more genes, because I don't think it was very, very huge number of genes from the beginning, and then we have narrowed it from the beginning to now. There are always new genes coming in to populations. So we always have some sort of evolution and some sort of development. But we don't know exactly today if we really have genetic erosion and degradation of our genetic systems. And all or most of our breeding systems give us inbreeding. So we will lose many genes. And all this we really don't exactly know about, because we cannot see the genes, we cannot count them, and so on. So it's difficult, but we can see the effects of it. And some of the effects are that breeding will be bad in for instance, cows. So the cows will not come into heat, and they will not be pregnant, and there are difficulties in delivering the calves and so on. And in these, you have diploid roles, And all these things you see that bees die and so part of this can be the effects of inbreeding and loss of genes. But we don't know because we have very, very bad records on all this. We should have to know of these things. So what I'm saying is just what we have to think about and work more about. And many of you have seen these classical fundamentals for gene frequency changes in populations. And it is mostly these four things. Migration is what? You know what that is? Yeah, there. Yeah. If they come from outside and come into, or they migrate out from our population. We have mutation, fixing new genes, and we always have mutation, but most new genes are more or less detrimental. So, but it will gain little influence of new genes. And of course, evolution will have used mutation in the long run. And we have those two important. Selection. That's what we do when we select a queen for breeding, or we select queens or colonies for drone production. And genetic drift. That is a thing we don't seldom think about when we are not geneticists. And that means that when we have very small populations, we don't know exactly what genes follows to the next generation, because so many genes are selected away, because we can just pick some of the individuals. Say we have 5 individuals. They just pick some of the genes which are available to pass it to the next generation. But if you have thousands of individuals, they will pass almost all genes we have in the population. So therefore, we don't know exactly which or what genes we are taking with us. And that's what we call genetic drift. We lose many genes, and we don't know what genes we lose. And this is important when we have very small populations. And this is part of the inbreeding problems. So you cannot, as some people think, by inbreeding, fix the genes and think that we will have a stable gene pool and producing stable types of individuals. So what we do when we have inbreeding is that we lose very many genes when we make some genes in homozygotic forms. That means that they are the two genes alike all over. So yeah, we continue. So if we go back to what we do when we breed, we have a honeybee colony or many colonies. And of course you know all this, but I have to say it anyhow. We have one queen in a colony, some 500 drones. We can have many more drones if we produce drones for mating station by putting drone combs and force the queen to produce more drones. Then we can have perhaps 2,000 to 3,000 or more drones in the colony. And you have about 50,000 workers, or you can have up to several hundred thousand in very big colonies. And what I think is very interesting and perhaps very important is that a honeybee colony has what I don't know if this is a correct word, but it has an eternal life. It can live in the same hole in the wall or in the tree for, say, 1,000 years. If nothing destroys The normal is that the queen will be some 2-3 years old. But some queens can be up to 6 or 7 years. I don't know, but they say they can be. So then we have what we can call a superorganism. And in this colony, it is a different way of thinking for us if we breed the bees and then shift the queen to a queen from outside, from another colony. In the normal, in the natural way of living, the colony always shifts the queen to a queen among the sisters. And so then we have an unbroken mother line through many, many, many generations. And as I see it, if we go to when the bees started to be bees, we don't know exactly when, but something between 5 million years and 75 million years old. The bees are of that age. We don't exactly know, but I found a picture just the other week, and they thought they had found bees that were some 70, 80 million years old. And they look almost as our bees. So they are very, very old, and in all this time, the bees have bred in their own way in this eternal maternal line. So we have bred bees in our way for a very, very short time, some 100, 150 years. Yeah, and bees are hermaphrodites and they are superorganisms. Superorganism is what we said just now. And they are what do you say, hermaphrodite or hermaphrodite?
Yeah, sounds good.
Yeah, and that means, from a genetical view, when you try to understand the genetics of bees, you have to see them as one queen is the mother and the other queen is the father. And the queen producing the drone is the father. And the drone is just sperm, it's gametes, you say in the genetical language. It's a sperm producing multiple sperms. So it's some people say that they are flying gametes. So I like to see them just as it's always two queens mating, and this makes it much easier to count inbreeding and relationships and such things. But you have the drones behind, and the drones are the sperms. Yeah. If we go back to bee breeding and what it looks like, we have talked about this a little bit earlier here. And you know that when the mating takes place, then the drones and the queens, they go to the so-called drone congregation areas. And we had a discussion yesterday about what this is really. And in the natural way of living, you have random mating between the queens and the drones. So the drones are produced from all queens in the neighborhood, and the queens go to these drone congregation areas and mate. And this means that the queens maybe, we don't exactly know if there is a selection in the mating, but if we suggest there is no real selection, then we have a real a random mating. And this means that you have the queen collect drones from, collect mating with the drones from a vast area. And it depends on landscape and so on, from where the drones come. And as you know, the queen mates with a large number of drones. And in all textbooks, the queen mates with some 6 or 7 drones. But we know that they mate with something about perhaps between 20 and 30, perhaps much more than 30 drones. And this means that within the spermatheca of the queen, there is sperm from many different drones, and the drones come from many different queens. So it is a wide variety of genes within the spermatheca of the queen. And this means also that the workers in a honeybee colony has a wide genetic variation between them. And I think this is a very important thing to discuss when we discuss breeding and queen production and so on. Yes, and then when we talk about this, we have also the sex determination system, and we have the sex alleles producing diploid drones, and these diploid drones, they are killed by the bees when they are about 2.5 or 3 days old. So it's like when they can see, when the bees see if they want to produce a queen, they produce a queen from larvae of about the same age as they killed the diploid drones.
What causes the diploid drones?
Pardon?
What causes the diploid drones?
Oh, yeah, they are drones. They are, you must say they are drones, but they are not really. They are lethal. They are killed. But when if you can grow, what do you say? You can have them grown up if you put them into a queen. What do you call it?
Queen cage?
Queen cage, yeah, so they can feed the drones, but they cannot kill them. And then the bees will feed them, and you have real drones from them.
But I'm asking, what's the mechanism that produces the diploid drone?
The mechanism, it is the sex determination.
Okay.
It's the sex alleles.
Okay.
You know about the sex alleles?
Right. If you have 2 of the same sex allele.
Yeah.
Okay. And
2 of the same.
and how many are there?
Oh, this is also, it depends on the population size, because big population can hold lots of sex alleles,
Okay.
and small populations can keep just a few of them.
Okay.
So if you have a big population, you can. It's not you will not have so many diploid drones.
Okay.
And these drones are normally killed by the bees because
They are killed as small larvae.
Uh-huh.
Yeah, because if they are grown up, then they will produce diploid sperms, and then they will produce, if they mate, and they can mate, they will produce triploid workers or queens, and they will have a very bad life. So it's better, as I see it. So the nature has made the choice to kill them as larvae because it's a cost for them if they are raised to mature drones. So yeah.
So a diploid worker or queen would be defective in some way? She would not I mean,
They're all
Pardon,
No,
once again.
triploid.
triploid.
Yeah.
Triploid, yes, they will be defective, yes. So triploid individuals will very seldom function. It's so in
So
most...
it's a waste of time to let them
Yeah,
happen.
it's waste of time and of energy and, yeah. So, and then, sometimes I'm talking about the paradox of the sex alleles. Many people think that the sex alleles are only bad because it will reduce the brood number. If you have many diploid drones, then there will be many holes in the brood, yeah. But it is there are studies showing that a colony can get rid of quite a lot of the brood without functioning in a bad way. But this reduces perhaps the colony's fitness. But the sex alleles also can, as I see it, this is one way that nature has selected to reduce inbreeding. Because when the inbred colonies produce these diploid drones, with these diploid drones, some inbred individuals will get away from the population. So this is one small way for the populations to reduce inbreeding. And this is a very, common method in plants to reduce inbreeding. So many plants have a system of alleles about the same as the sex alleles, reducing the number of seeds, produced seeds that are inbred. So this is about the same system. And they can call this system self... Ska jag komma ihåg vad de heter, alltså de här S-allelerna på växter. There is a certain name of these alleles, and they are very common in for instance, in neem trees, yeah.
Pine trees.
Pine trees,
Yep.
yeah, and some things. So this is very common. If you read some genetic books about breeding trees and such things, then you will put with this type of alleles. Self-sterilization
Yep.
alleles, yeah, that's the name, yeah. Yeah, and then if we go back to the picture where I showed number of drones and number of queens in a colony, then if we use this knowledge and to understand which individual in the colony is the most important if we want to breed to make a change. If we breed cows, for instance, then everybody says the most important individual is the bull. And why is the bull the most important individual?
Because he
Can
can,
anybody say?
because he can fertilize so many females. He has more of an impact on a bigger population.
Yes, exactly. And then, why do people think that why should the drone be the most important? Question? Anybody?
For-
I'm sorry.
Go ahead.
It would be again because her genetics are affecting the majority of the population. As
Hold on,
opposed-
once.
Her genetics are affecting the majority of the population rather than the drone.
I couldn't follow what you said. Yeah, I think you said, yeah.
Well, like with the cows, the male is affecting the majority, in the opposite, it's the
Yeah.
queen. 'cause
Exactly.
her- Yeah.
Exactly, I couldn't just follow
Oh, that's
her.
okay.
It's difficult to hear
Talk to
the
you.
pronunciation sometimes. Yeah, that's correct. That's correct. So queen can produce how many? 2,000, 3,000, 10,000 offspring queens if you're
If you're a bee breeder.
if you're a bee breeder. Yes, and I put the larvae in cell cups and so on. Yeah. But the drones from one queen cannot fertilize more than 10, 20, perhaps some more queens. Because we know that queens mated by 20, 30 or even more drones. And we know also that you need many more drones on the mating phase in order to have good mating on the queens. So you must calculate at least 50 drones or more per mated queen, even if she is mated to only half that number. So that it must be some excess of drones. So, as I see it, if you want to make a good breeding, then you should breed on the queens. Yeah. So this is what this picture says. So my view of this is that if you have some 100, 200,000 of honeybee colonies, and all these have queens of good nature, then of course these queens will produce good drones. So then you can select the good queens, and there are many models for doing this. You can either select a few number of queens and breed a number of daughters to requeen all these colonies, or you can just take away the worst queens, the bad ones, the most swarming ones, the meanest ones, and so on, and then rely on selecting part, say 25% of the best queens to breed and make them in your own place. And of course, since your or your neighbor's bees produce the drones, why go to a mating place and why buy starlines or midnights? Do you have midnights queens nowadays? I thought they were dead since 30 years. Are the midnight queens?
They quit making them some time ago. Yeah.
Pardon?
They no longer make them.
No. I think midnights, they were mean, weren't they?
They were supposed to be.
No,
They were supposed to be.
midnights are very, very gentle.
Not the midnights we get to Sweden. They were black and mean. Yeah. I remember that.
They came in from Norway with the Vikings.
Yeah. Oh, yeah. So this is really, this is my way of seeing this. So, but people always rely on buying queens. It's like what other people have is always better than your own. So why don't try to breed your own and really rely on that? Yeah, we will continue. See what I have more. Yeah. I'm very interested in a sustainable way of keeping bees and of keeping biological variation. So I think that natural breeding structure is good because we keep a very growth or wide variation within the colony and within the population. Then the population can keep many genes. And the artificial mating structure introduces this genetic variation very, very quickly and very profound. So in a few generations, you can reduce this from very, very big to very narrow. What you reach with the modern bee breeding models is increased relationship within the colony. The workers will be very closely related. And if queens born in related colonies, and if they then mate, so if related individuals mate, then we get inbreeding. And this gives genetic erosion. That means tattle genes. And perhaps non-sustainable beekeeping. I suggest so. What I have been studying and found out in my work is that the typical things in a naturally breeding honeybee population is that due to the system of drones and queens, drones are one generation older than the queens. Then you have always overlapping generations. Discrete generations we have in animals, in mammals, for instance, where you can, in reality, you have also overlapping generations. But you can have discrete means that mother and father belong to one generation, their offspring belong to the next, and the offsprings mate between each other, and so on. And then you have discrete generations. And overlapping means that individuals from different generations meet in mating. And when you have overlapping generations, then this effective population size will increase, that I talked about earlier. So this is a way to keeping a little bigger genetic variation. And the queen collects sperm in the spermatheca. And that is a very smart way of keeping the variation. Because if many colonies are killed during the winter, then the few that survive, they keep very big genetic variation inside the spermatheca. So the next generation can partly recover the old population. And I haven't put this in here, but you know also that in every colony there are some, say 5, 7, 8, 9, 10 workers producing drones. You always have worker-produced drones in the colonies. And if you have very many colonies killed during the winter, then some of those workers will produce drones. So then you will have both drones and females from these colonies. This way you can restore the genetic variation. So I think that's why nature has told some of the workers to produce drones. And this is also an interesting thing, because in mating stations, people say that all the drones in the mating stations are always produced by the few queens. produced for producing drones. There are always some few drones coming from the mating colonies, from the mating nuts. So, and I think this is very good for the nature's way to see genetic variation. And since the beekeepers or the queen breeders don't know this, so they say this works good. Yes, thank God it does. But it's not thanks what we think. And yeah, we have talked about sex alleles and multiple mating. No. Yes, and the first guy talked about the queen replaced by a daughter. That's what I think is supersedium. That one queen is replaced by a new queen. But as I see it, if you don't see this as a bad thing, then if each queen of a population produces a daughter each, then you will have a very good, a very big gene pool. As far as you select, the gene pool will be reduced. And we call this family size variance. This means how different the family size are from different families. So if some families, that means some queens have 0 offsprings, and some have say 2 or 3 offsprings, and some have 1,000 offsprings. Then you have a very small family size variance. No, we have a big family size variance. And this is big. And if every queen has exactly 1 offspring, then we have a small family size variance. They are exactly the same. So this is a good way of keeping a big genetic variation. And mating structure, colony structure, we have talked about that. This is selection and such things. Yeah. Relationships in a colony. When you calculation relationships in a colony, you must know how many, or on an average, how many full seed groups you have, how many half seed groups, and super seed groups. And the super seed group, that means the sisters produced from 1 drone, and they are related to 75%. That means that they are very highly related. And half sieves, no, it's wrong, it's wrong, it's wrong. Full sieves are 50% and the half sieves are 25% sieves. That means among ordinary sisters and brothers of people, if they have 2 parents in common, they are full sieves and are related on an average 50%. That does not mean that all of them are. And yeah, so I have to change this. Half sieves means that 1 parent is common and the other is different.
And I'm sorry, I didn't quite understand. The super sibs are.
They are from 1 drone. 1 drone.
Since drones are haploid, then you've got exactly the same contribution from the father as opposed to humans where you've got possible 50. So since it's always the same from the father and it's half from, and it's variable from the mother, then it's 75%. Does that make sense?
Yeah.
See that? Does that make sense? Okay.
And we're talking about drones here?
No.
Or we're talking,
Sibs is siblings.
Siblings.
but I mean, are we talking about worker siblings or drone siblings?
No, always worker siblings.
Always
Yeah.
worker
Yeah,
siblings.
it's because drone, if you say drone siblings, then they are it's the sperms from
They never
from
separate.
single,
Oh.
that's the gametes, that's the, yeah. It
Because
comes
they
from-
don't get anything from they just get an unfertilized egg, so they're just getting it from the mother.
Yes, they are always getting it from the mother, but it passes through or via the drone. So the drone is comparable with a sperm, but since the drones can produce many siblings, then you can have sisters with the same drone as a sperm or a father, but it isn't correct to call it the father, because the drone producing queen is really the father.
Right.
So this means that all these half of the genes in these sisters are exactly the same. They are twins on half part, and they are ordinary sisters on the other part. So in full, you have to see these opposites.
Right.
So a full sib has exactly half from the father and half from the mother. And when you compare several, then they are, yes, they have on average half from, because it's not always the same half of the mother. So it can happen, theoretically it can happen that ordinary full sibs are not related at all, and they can be as much as twins, but most of them are around 50% related. So that's why some people get kids who are somehow like twins. They are so alike, and sometimes they are just as from different planets. Yeah, and but they have the same parents, but perhaps they are not that much related. Can you follow it? Yeah. Yes. So if we calculate these relationships within a colony, I have made a calculation that on an average I can say they may be related as much as 0.30 or 0.35 if they are not much, if the population is not too close. But if we use a mating station, this relationship within a colony will increase very quickly. Even if the mating station contains drones which are not related to the queens put there. So it depends on just how the genotypes of the drones. So if the few mating drone producing queens put on a mating station, if they are produced on a mating station, then the next generation they will be very close related, and then they will be more and more closely related. So very quickly we can have them more than full sibs within a colony, and that comes very quickly if you systematically use a mating station. And I think this is very important, because I don't think people is aware of that. And what happens of this, I don't know exactly. But there is need for recording of matings and what you find out in the bee apiaries, among the beehives. But we don't know much of all this. Yeah, and if we just say what all these words mean, relationship means in a scientific way, means the number of common genes between two compared individuals, how like they are. And inbreeding means the number of identical genes within an individual, the degree of homozygosity. One thing that I have been working with and thinking of very much is what I call biodiversity loss. And you have heard much of this, I suggest. And this is loss of experience collected and accumulated in the genetic structures of species during millions of generations. And when we then reduce this variation, we reduce this inherited experience, and it takes a lot of time to get it back again. So it's very difficult to think of restoring genetic diversity. This is what we have to, we can take these pictures. So when we have discussed all these things, I have two pictures of this, of natural beekeeping and sustainable beekeeping. So if we want a sustainable beekeeping, I think it's important to look under these special characteristics of bee breeding structure that we have discussed just now. And how the queen is replaced. I say here queen lineage intact. I don't know if that's a good way to say it, but that means that the queen is the daughter of a queen, and so far in their colony. They haven't left their colony. You can follow it back a million of years, perhaps 2, 3, 4, 5 million of years. They have lived in their own colony, and then, of course, some colonies die and they swarm and so forth, but they are reared in their own colony, and then they have swarmed. But no queens have been put between other colonies, queens' colonies. They have always lived in their own colony. And bees have lived in intact natural existence for 50 million years or more. And then what we talked about earlier, overlapping generations and colony structure gives a memory of the colony. So since the bees have lived in the same colony for several generations, there is some sort of a memory inside the colony. So if we break this memory and we make small nuts, or what you call it, put new queens in them, they have no history behind them.
And
they are just put,
You're talking genetically memory. You're not talking about a
yes.
communication
Yes,
within the worker.
yes.
You're talking genetics.
I'm talking more about the communication, phenotypic memory,
right.
the environmental things.
Not that the bees are used to the daisy patch being 2 miles away.
No, that just that the colony, you said it yourself. It is not the genes only. It is.
It's also social or communication.
Yeah.
Okay, that's interesting.
They can recognize the pheromones and so on. And I think this can be important to discuss anyhow in the future. And colonies can live forever. And swarms, of course, replace dead colonies and extends their populations. So we need swarms so the bees can expand in numbers. And what we have done in about little more than 100 years, we have breed queens and grafting a larvae, all these things we have heard about. We are mating, confined in small mating, and it concerns pheromones and temperature and many such things. We have mating stations with few sisters, giving related individuals. And we sell and buy mated queens. Yes, and I don't know how to explain this, but the mated queens are placed in an alien colony without the continuity of colony lineage. And then I say memory. So all these things, I think, can be important to perhaps explain at least part, a little part of the colony collapse disease and such things. I really don't know, but I think somebody has to tell this, say this. And I'm convinced it's part of it anyhow, because we are not allowed to track down the biology in the way we really do. So afterwards I will be killed by all the queen breeders. Thank you.
Last summer, I was told by a scientist that all the